In section 10.6, we're going to look at polar equations of conic sections, and we'll talk about Kepler's laws just for a moment. Not too much, but we'll talk about Kepler's law for just a second. Most of this is going to focus on polar equations of conic sections. Now, we saw earlier when we dealt with the standard form of conic sections, that the eccentricity of these conic sections sort of tells me what type of conic sections it is. So when we're looking for an ellipse, we want an eccentricity that's between 0 and 1. When the eccentricity is 0, we saw that we got a circle. You can think of that as a special case of an ellipse, or you can think of that as different than an ellipse, whichever you'd like. A parabola has eccentricity of exactly equal to 1, and a hyperbola has eccentricities which are greater than 1. Again, different hyperbolas are going to have different eccentricities, but they're all going to be greater than 1. So what the polar equations do is they define based on eccentricity. So eccentricity comes up when you're creating these polar equations of conic sections. So the other thing that we do with these polar equations of conic sections is we're going to force the focus to be at the pole. All right, so what we would normally call the origin, we're going to put the focus at what we usually call the origin or the pole. And if we do that, if we allow ourselves to force the focus to be at the pole, then polar equations of conic sections can always be written as r equals either ED over 1 plus or minus E times cosine theta, or R equals ED 1 plus or minus E sine theta. Now, the E is obviously the eccentricity. Notice that shows up in 2 spots, whichever equation I use. The only other thing that we have in both equations is this letter D. And this letter D actually tells you the distance between the directrix and the pole, okay? So the distance from the origin to the directrix. And yes, I know we only looked at directrix when we talked about parabolas, but any conic section will in fact have a directrix. We're not going to go through all of those things right now, but that's the idea. So what we're going to do is we're going to take equations that are written either as that form or similar to that form. And we're going to sketch those. We're going to look and find the eccentricity and find the distance from the pole to the directrix. Okay? And then also we'll do the reverse. We'll take and look at the we'll create the equation given the eccentricity and some other properties. So let's take a look at this first equation here. R equals -4 over 1 minus cosine theta. So -4 over 1 minus cosine theta. That already, you can see, looks like R equals ED over 1 plus or minus E cosine theta. Now, in this case, it already fits the form essentially perfectly, where our E is obviously has to be the coefficient of this cosine, so it's -1. Usually we let E be the positive number, so that's why we have either the plus or the minus option. We usually let E be positive, so we let E be +1. And the D, the distance between the pole and the directrix, well, if ED is equal to -4, let me write this down. ED is equal to -4, and E is equal to 1, then D has to be -4. So there you go. This equation is the equation of a conic section whose eccentricity is 1 and where the distance between the pole, again, we think the origin, and the directrix is -4. Okay. By the way, because the eccentricity is 1, we also know that this has to be a parabola. So when we graph this, we should expect to see a parabola because the eccentricity is exactly equal to 1. By the way, I have already graphed this. R equals -4 over 1 minus cosine theta. And you can see here that you, in fact, do get the parabola that I was talking about. Now, by the way, if you get a point on this parabola, what will happen is it'll come from over here as theta equals 0. Well, theta equals 0, this is undefined. This equation is undefined. You can calculate that as by yourself. And then obviously, as we get these angles, our point comes around. I think it comes this way, touches this when theta is equal to pi, and goes back around. I forget if it goes around this direction or that direction, but you can see it gives you a parabola. And you can also see that the distance between, it says, the pole and the directrix, we said is -4. Well, let's take a look at the equation. Since the pole is at the origin, 0, 0, let's think about what that means for the directrix. That means that the directrix is the equation x equals 4, all right? So that from the pole to the directrix is a distance of 4 or -4, depending on which way you're going. You technically should always go from the directrix to the pole. So that's why we get that -4 there. So that's what's going on. Now you can play with this a little bit and see what happens as you adjust these numbers. If you adjust the negative cosine to a positive cosine, we just change and point the opposite direction. By the way, you also change and point the opposite direction if you change that -4 to a +4. And notice that the cosine, it gives you the conic sections which point left and right. If I would have switched to sine of theta, that would have given me the conic section, or at least in this case, the parabola that points up or down, depending on whether I had positives or negatives. So hopefully that all makes sense. Now, what we're going to be focused on is just that, finding the eccentricity, finding the distance from the pole to the directrix, and then being able to sketch if we have to. Mostly when I say sketch, I just mean graph on your calculator. Okay, so let's go ahead and do that if our equation doesn't perfectly match up. So let's look at this equation, r equals 6 over 2 plus cosine theta, and let's find the eccentricity and the distance from the pole to the directrix of this conic. And to just verify that you got the right thing, sketch the graph. Why don't you go ahead and push pause on the video and I'll come back and do that. So we can see that this one does not fit this form perfectly. Namely, I don't have a 1 here in front. So in order to fit this form perfectly, I have to have a 1 here in the denominator, in this spot in the denominator. In this equation, I have a 2 there. And so obviously what I have to do is some algebraic manipulation. Basically, the easy way to do this is to take each side and multiply it by a half on the top, a half on the bottom. So we're going to multiply both the top and the bottom by a half. That's going to give me 3 over 1 plus 1/2 times cosine theta. So now it's in the form I want, and now I can start reading off what I want. Again, the number in front of the cosine here is my eccentricity, so my eccentricity is 1/2. E times D we see is the numerator, so E times D is 3. E in this case is 1/2, so you can replace, replace the E with a 1/2. So E times D is 3. That means that the distance from the directrix to the pole is going to be 6. And because E is 1/2, that's a number which is between 0 and 1. Therefore, what we're dealing here is an ellipse. Okay, it's an ellipse with eccentricity 1/2, where the distance between the pole, again the origin, and the directrix is 6. Let's go ahead and graph that. So here that is. I've graphed the ellipse. By the way, I use the original form of the equation, 6/2 plus cosine theta. You can see that this is an ellipse. One of the foci, I should say, a focus, is at the pole, the origin there. And then if you're looking for the directrix is out here at x equals 6. Again, we didn't talk earlier about the directrix of an ellipse, but there is such a thing. So there we go. All right. Interestingly enough. So I'd like you to push pause on this video and try to do the next one. Same thing, use some algebraic manipulation, find the eccentricity, the distance from the pole to the directrix, and then sketch the graph. You went ahead and did those. So here we go. So the problem here is that we have a 5 instead of a 1. By the way, this works the same. This is the same equation whether I have cosine or sine. Doesn't really matter. So we go, it matters the way it points, obviously, but it doesn't matter in the process. So 1 plus E sine theta, we need a 1 here, so that means we need to multiply top and bottom equation by 1/5. If I take and multiply 10 by a fifth, I get 2. If I multiply 5 by a fifth, I get 1. If I multiply 4 by a fifth, I get 4/5. So this is the same equation as 2 over 1 plus 4/5 times sine theta. Now that means that the eccentricity, the coefficient of my sine, is 4/5. By the way, that means I'm dealing with an ellipse, right? We know E times D has to be the numerator. And by the way, again, don't forget it's the numerator of this equation. It's not 10, but rather 2. So make sure it's the numerator of your final equation there. So E times D is 2. And so if I take 4/5 times D equal to 2, I'll multiply both sides by 5/4, you get D is equal to 2.5. So the distance from the pole, the origin, to the directrix is 2.5. By the way, if you look at this compared to our last one, let me actually compare these two using a graph that you come up with. Remember, in our last problem, we had 6/2 plus cosine theta. Notice that was oriented left and right. In other words, it was stretched out more left and right than it was up and down. And in this problem, 10 over 5 plus 4 sine theta, this is stretched out more up and down than it is left and right. And that's sort of telling you the cosine versus sine arguments. Now, the other thing you see is that this purple curve is stretched out further than the red curve. And that has to do with the eccentricity. If you think about the eccentricity of the red curve had eccentricity of 1/2. The purple curve has eccentricity of 4/5. So again, the closer you are to 0, the closer to a circle you're going to be. The closer you are to 1, the more stretched out you're going to be. So since purple had eccentricity of 4/5, that's closer to 1, it's stretched out further. By the way, just as a note, what did we say as our distance from the pole to the directrix? Let me cancel this one out. Our distance from the pole to the directrix was 2.5. Obviously, in this case, that's going to be a y equals 2.5. And so that is the directrix. By the way, obviously, directrix is halfway between your focus. Did I say this incorrectly? So halfway between the focus and the directrix is one of your vertex, is a vertex, excuse me. So there we go. So what I'd like you to do a couple more of those. So I want you to do example 4 here on your own. Push pause on the video. All right, so we want to match this thing. What we need to do is multiply both the top and bottom by 1/3. If I do that, -6 times a third gives me a -2. 3 times a third gives me 1. 7 times a third gives me 7/3. So I get -2, 1 plus 7/3 sine theta. That means the eccentricity is 7/3, the coefficient of sine there. E times d has to be equal to -2. And since E is 7/3, that means the distance from the focus to the directrix has to be -6/7. Just multiply both sides by 3/7. And by the way, the eccentricity here, obviously, since it's greater than 1, this conic section has to be a hyperbola. And we can see that when we graph it. So there we go. Here is that hyperbola. You can zoom in or out. By the way, again, since this hyperbola has sine in it, the hyperbola is pointed up and down. If the hyperbola would have had a cosine, we'd have been pointing left and right. All right. So that's the idea. You can, by the way, play around with your trace feature on your calculator, and you'll see how the dots go, depending on which way you're going, up or down. You'll see that the dots trace around and go up and around in some interesting ways. All right, let's do one more of those, just so that we've dealt with one more type of situation. I want you to find the eccentricity, the distance from the pole to the directrix, and then sketch the graph. Also tell me whether this is an ellipse, a hyperbola, or a parabola. So go ahead and push pause on the video and do that. The thing about this is you have to be careful that since we have a -12 and we want a positive 1 to be in this denominator, we need to make sure that when you multiply top and bottom, it's not by a 1/12, but rather by a -1/12. And so when you multiply the top by a -1/12, you get a -25. When you multiply a -12 by -1/12, you get a +1. And when you multiply 6 by a -1/12, you get a -1/2. So our r equals -25 over 1 minus 1/2 sine theta. That means the eccentricity is 1/2. E times d is -25. If E is 1/2, then that means d has to be -50. Eccentricity of 1/2 is between 0 and 1, so that's an ellipse. So that's how we do that. Now, one thing I want to mention before I get too far is what happens. I don't need to graph that one. If you want to graph that one, go ahead and graph that last example 5. One of the thing that I wanted to mention, what if the eccentricity is 0? So if the eccentricity is 0, Well, let's give an example here. Let's do ED over 1 plus E sine theta. What's going to happen to the bottom and what's going to happen to the top of this fraction? Well, in the denominator, we're only going to have a 1 because 0 times sine of anything is just going to be 0. And in the numerator, we're going to end up with 0. So that's why in the very beginning, I didn't deal with the circle at all in this format, because if we have the circle where the eccentricity is exactly equal to 1, well, then these equations kind of don't make any sense. It's just r equals 0, which is just the point at the pole or the origin, however you'd like to say that. So when e equals 0, we don't mess around. So you're never going to see a circle written in this format. Okay, in fact, we already know the format that we can do a circle. Just do r equals a number, and that gives you a circle of radius, whatever that number is. For instance, if I have r equals 10, I get a circle of radius 10. So there you go. That's how we deal with these equations.